Hello, you're welcome back. So this is the second video on linear regression. In the first video, I explained to you what linear regression is and how we use it to make predictions. I also established that a linear regression simply has two properties that we call parameter. One is the intercept, usually called beta naught or theta naught. And the second one is the slope, what we call beta 1 or theta 1. Then I explained that to understand if a model is suitable, you need to know that it has the least error. And that error could be expressed in terms of the absolute error. It could be expressed in terms of the squared error or even the root mean squared error. Okay. So regardless of the kind of error you are trying to use, make sure it is the least. And then how do we actually find a model that has the least error? Well, to have a model that has the least error, we need to use a value of beta naught and beta 1 that can help us to minimize what we call the cost function. And then the question goes to, how then do we get the values of these beta naught and beta 1? So and that's what we'll be treating in this first video. So the method we can use to obtain the value of the beta naught and beta 1, one of them is what we call the ordinary least square error, popularly called OLS. So what that is that when we are talking about ordinary least square error, we will come back to this equation right here, where we simply said that L equals to y minus b naught minus b1x, okay, which is equation 4, right? So let me pick this equation, Control C, and then I can simply just paste it right here so that we can see that. To make this equation, this actually what we have here is just loss function, okay? Loss function. To transform this to a cost function, let me call cost function J. To transform this to a cost function, we need to do a summation of all of that. So we will have like summation of this y minus b naught minus b1 x then squared. So the difference between a loss function and a cost function is that a loss function is simply the loss of a particular observation. Then a cost function is the function of all of the observation, that is all of the data sets, all right? So, but then regardless, it's still the same kind of equation, all right? So in here, I would say that my cost function, so to make it easy, we usually say that J equals to y minus b naught minus b1 x, okay? Actually, it should be big X, because this now, what I'm talking about right now is cost function. So it is all of the feature, okay? So it is like big X. In this case, what I just did was to remove this summation. I removed this summation, and then I removed this absolute symbol. But I mean, I don't want to carry it over, but at the same time, it's still the same thing. Okay, so this is the cost function in a very reduced manner. But now, going back to the concept of ordinary least square error. Well, ordinary least square error identifies that in order to have, let me put it this way. What we are trying to do, we are trying to look for the value of b naught and b1, right? But there is a clause. We want to get the value of that b1 and b naught that will help us to minimize this cost function, right? So in order to do that, the ordinary least square error will simply say, okay, how about we take the gradient of this function with respect to each parameters? So we can say with respect to b1, and then we equate to 0. We do the same thing, we take the gradient of this parameter b naught, and then we equate to 0. Now, when you equate these two, so that means this function here, you have to look for the partial derivative. I would not calculate that because we will still do that in the next method. So I don't want to have a lot of repetitions. So if you do the partial derivative of this equation and you equate to 0, you do the partial derivative of this same equation with respect to b naught and you equate to 0, and then you solve analytically, you will arrive at a closed form equation that we usually write as b equals to x transpose multiplied by x, and then you get the inverse of this, then you do the dot product of x transpose with respect to y. Okay, so this here is the closed form equation of the ordinary least square error. I am not proving the equation, obviously, I just like wrote it out. If you are very interested in how this equation is proved, I will just suggest you check online and see for a lot of textbooks on ordinary least square error. But the concept here is not to prove it, but just to see how we can apply it, okay? But then this is the closed form, exactly. So when you say something is a closed form, you need to break it down, right? So in this concept, B is not B naught, it is not B1, it is simply beta, okay? And then X is, you know, the big X. So if I break this down here, the B that we have here, B is a vector. It is a column vector which comprises of B nodes and B1. Okay, and then X is also a vector, that is the feature vector. So it will comprise of a series of 1 up to, let's say, n. And then in our case, where we are only dealing with just one feature. So that means that we have x1, x2, x3. In this case, there will be small letters, right? That's it. And then X transpose, well, X transpose is just to transform this equation into transpose. To do transpose, it simply means you convert the column into rows, okay? So this will simply look like this. Let's see, 1, 1, 1 up to n. And here we'll have x1, x2, x3 up to xn, right? Then you can just put the matrices symbol here. Control Z. Let me swipe this to the right a little bit. Okay, and then you will have the matrices symbol here. And then y is simply a column vector as well, which comprises of y1, y2 up to yn. Well, I'm sure you remember that our n equals to, oh, now I don't remember. I think our n equals to 919 because initially our n was 1030. Then after we did all of the cleaning, we removed the outlier, we removed the a lot of things, we were able to get down to 919. So I think our n is 919 if I'm not wrong. Then, okay, if you also want to do the inverse, okay, inverse, you could see there's something we call inverse right here, right? So inverse, say for example you have a matrix. So inverse, say for example you have a matrix A that looks like this: small a, b, c, d. If you want to do the inverse of A, you can simply just say 1 over determinant. So you look for determinant. Determinant is represented as D. And then D is simply when you multiply this A times D. So you do like AD minus, then you do B times C. So you do BC. All right. Then you switch B and A. So you can have D here, you can have A here, then all this becomes negative. So you have minus B minus C. So that is how you look for inverse of a matrices, okay? So when you have to transform the X transpose multiplied by X and you have to do the inverse, this is somehow it is done, okay? As I said, I am not going to prove all of this. I'm just writing how the equation looks like, okay? And then I broke it down so that you know the identity of each matrices. So this equation that we have here, let me copy it, Ctrl C, and then I maybe paste it here. So this is the major equation of OLS which is ordinary equation. So I will say closed form equation of OLS. But then in our case, where we only have one feature, it will look a little bit complex if we just dive into matrices and vectors just like that. Because we are working with just one feature, it's more or less like an algebraic equation, so it does not really require matrices. So this closed form equation can be broken down, okay, for one feature. When you have two features, then it becomes 2D. So 2D, that is vector already. You cannot do without, So when you have 1D, it is like scalar, not scalar per se, but 1D. But then when you have 2D, it becomes 2D vector. When you have 3D, it becomes a matrix, 4D, it's just 4G matrix, So in this case, we have one feature, I will just write down the simpler form of this equation. So to calculate B1, which is our slope, B1 is usually given as summation of x minus x bar. X bar means the mean. Then you multiply this with y minus y bar. Y is the target and y bar is the mean of the target. Then you divide all of this by the summation of x minus x bar. Then you square this. And this is the value this is the formula for your B1. Also, the second parameter, which is beta naught. Beta naught, remember that the equation of linear regression looks like this. B naught beta 1x. So now imagine that in this case, this is x bar for this case. Now imagine that we already have the value for beta 1, which is this equation. This and this are constant. Now, if we make beta naught the subject of the formula from this equation, if I make beta naught the subject of the formula, I will simply have y bar minus beta 1x, right? So I would have y bar minus beta 1x bar. So this is quite the equation. So let's call this, let me just circle it out, okay? Let me change the ink, okay? All right. All right. So what this simply means is that if we apply this formula by looking for x minus x bar multiplied by y minus y bar and all of this, if we apply this formula and we get a value, that value gives us beta 1. We also apply this formula, we get a value. That value is called beta naught. What OLS method is telling us that these values that we get from this equation, if we insert them into the linear equation method, which is b naught plus b1x, big X, I'll use big X. If I obtain the value of beta naught and beta 1 from these two equations, and I put them into this equation, what OLS is telling me that this will become my best model. The value that I get, B1 and B0, they will be the value that will help me to minimize my loss function. So any other value that you use will not be the perfect parameters, okay? So in order to obtain the perfect parameters, you need to use these two formulas if you have one feature. I repeat, this is only applicable when you have one feature. When you have more than one feature, you have to use the matrices form, the vector and matrices form, okay? But when you have just one feature, we can simply use this. So this is what OLS method is. So OLS method is just an approach of determining B1 and B0, beta 0 and beta 1 in an analytical way, which is an exact method. So when we apply this equation and then when we get this beta 0 and beta 1 and we put it inside the linear equation method, it will help us to make the better predictions. Okay. So now the next step will be to code this up. We need to be more practical, because we don't want to dwell so much on the theory. We will pick one feature from our actual data, probably anyone, and then we will write this code in order to make the prediction, and then we can see for ourselves how this can be implemented in Python. So see you in the next video.